Arches have lots of fun properties. For example, even though they look like curved beams, they carry load a completely different way.
Beams carry load by bending, and this one cannot even support the weight of 2 wood blocks. This curved beam also works by bending, and despite being curved like an arch, it still cannot support the weight of 2 wood blocks. However, if we support the ends of this curved structure so that it can carry compression, it can suddenly support 2 wood blocks with ease. If the curved shape is cut into pieces, no meaningful bending is transferred from one block to the next. Instead, the blocks can only transfer compression to their neighbors. If we reconstitute the arch, only compression is transferred from one block to the next, and yet the arch is still able to carry 2 wood blocks. To further prove that no bending is transferred from one block to the next, we can put a roller between any pair of adjacent blocks, and the arch still stands. Isn't that cool? To better understand how an arch gets its strength, consider a piece of cloth. It cannot even support itself. However, if we allow it to take a curved shape like this, it can carry a substantial amount of load. And it does that because tension flows along its curved shape.
Arches work the same as this hammock, except that their shape is reflected upside down, and they carry compression rather than tension. Another popular misconception about arches is that they need a keystone. By a keystone, we mean a tapered stone at the top of the arch. Our model arch was purposely made with an even number of segments so that there is nothing in it that could be construed to be a keystone. Here's another fun thing. Did you know that some arches will collapse if load is removed? Just like a teeter-totter, arches require the forces acting on them to be suitably balanced. For example, this arch can carry heavy loads if they are suitably balanced. However, if we remove one of the loads, the arch fails catastrophically. It's a little tricky to explain why this happens. Our Arches and Chains video shows that for an arch to stand, its corresponding chain system, when reflected, must lie inside the profile of the arch. Here is the chain system corresponding to the original arch. The chain and weights have been chosen so that their weights are proportional respectively to the weights of the arch itself and the containers of marbles. It is thus a true representation of the arch. As you can see, the arch passes this so-called chain test. If we remove one of the side weights, the new chain shape does not lie inside the arch profile, and the chain test fails. When we remove the corresponding load from the arch, it does indeed fall down. Can you picture how the chain will change shape if the middle weight is removed? Will the arch stand or fall? Removing the middle weight produces a chain shape that falls outside of the arch profile, and the corresponding arch collapses. You might be curious how this arch from our other video can stand. It is easy to show that this arch passes the chain test, and that is why it stands. If we add weights proportional to the external load, the arch passes this modified chain test, and that is why it can still stand.
And here's one last thing. Many people think that a semicircle is a good shape for an arch, and sometimes it can be. However, thin semicircular arches like this one fail the chain test and fall down.
To learn why they can still sometimes be used, you will have to watch our other video.
Thanks for watching.